Warning! The video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. In this video, we're going to continue forward with graphing using calculus into our third big example. And it is assumed you've watched the beginning of this series so that you know what all the how-tos are here. I'm just going to jump right into the problem. Now, each of the examples that I'm doing in this video series they're handpicked for very special reasons. They each kind of showcase a different behavior. This one specifically has a really neat behavior to it I kind of dig. So here we have this. We're supposed to graph this function. Let's go ahead and start by talking about its intercepts. So y-intercept. Let's see. Can you let x equal 0? Is the big question. And the answer to that is no. Because if you try to let x equal 0, you'll get a -1 underneath the radical, underneath the square root specifically. So we don't have any. It does not exist. Or none, whatever you prefer. X-intercepts. Okay, so this is a tricky one. Because normally your x-intercepts occur when given a fraction, when your numerator is 0. So you would think, we have an x-intercept at x equals 0. But when you try to compute the y value, you realize you'll have the square root of -1 in that denominator. So therefore, there are no x-intercepts. Again, just try it. You will not find x-intercepts for this function. So we move on from there. The domain, which actually will help us understand why we don't have x-intercepts and why we don't have a y-intercept. The domain of this function, I'll do my work in blue. You can easily see that our domain is restricted because that denominator. We don't want the x squared minus 1 to be basically 0 or negative. So we need x squared minus 1 to strictly be positive, or in other words, we need x squared to strictly be greater than 1, or in other words, we need x to be greater than 1 or x to be less than -1. That is, our domain is the interval from -infinity up to a -1, union the interval from 1 to infinity. Again, x cannot equal 1 because you get division by 0. All right. Now we move up the algebra chain. Let's talk about symmetry. Let's go ahead and test this function for symmetry. I'll take a look at y. I'll call it y of x. So y of -x is equal to a -x over the square root of a -x being squared minus 1. Of course, -x being squared is x squared. And so that's a -x over the square root of x squared minus 1, which is the opposite of y of x. That is, y is an odd function. So it is odd. Which means I only have to graph the right-hand side accurately, and then I'll rotate it about the origin because it's symmetric about the origin. Now we go into our behaviors, right? The vertical asymptote, horizontal asymptotes. Vertical asymptote. Well, we do have domain issues here. Specifically, as x gets really close to 1. Remember, I'm going to use the fact that it's odd, so I'm not going to worry about the negative interval. I'm just going to worry about the positive interval. So I'll take a look at the limit as x approaches 1 from above, because in this interval, your x values are getting close to 1 from above, not from below. So what does that look like? Well, let's take a look. Of x over the square root of x squared minus 1. That would be a conceptual limit where the numerator is approaching 1 and the denominator is approaching 0, but from above, because it's 1 from above. 1 from above squared is still 1 from above. Minus 1 is positive. but close to 0. Square root of that is still positive and close to 0. And we know this limit will be infinity. So we have a vertical asymptote at x equals 1, and the behavior is that it goes to infinity. So x equals 1 is definitely a vertical asymptote, and the behavior is that your function goes to infinity. Now, horizontal or oblique asymptotes. Let me just state it right now. Again, just to remind you, you would have an oblique asymptote if you had more than one term here, and one of those terms tends to disappear as x goes to positive or negative infinity. Or if you can break this into two terms where one term goes to 0 as x goes to positive or negative infinity. But that can't happen here, so I don't have an oblique asymptote. However, I do have a horizontal asymptote. How do I know? Well, because I've done calculus. So let's go ahead and take a look. I don't worry about x going to negative infinity because it's an odd function. I'm only truthfully worried about the right-hand side of the graph. That's a huge thing that, honestly, I often forget to include, is the fact that I'm dealing with an odd function. I don't have to do 100% of everything. I could do half the work. So let's take this limit as x is going to positive infinity of our function, which is x over the square root of x squared minus 1. Well, that's the same thing as the limit as x is going to positive infinity of x over the square root of x squared times the square root of 1 minus 1 over x squared. That's just me factoring out an x squared out of that radical in the denominator. And normally the square root of x squared would be the absolute value of x, but x is going to positive infinity, so I don't have to worry about that. It's just x. And therefore, this turns into the limit as x goes to infinity of x over x, which cancels 1 over root 1 minus 1 over x squared. And that 1 over 1 minus x squared, no, I'm sorry, that 1 minus 1 over x squared. The 1 over x squared tends to 0 as x goes to infinity. And so you get 1 over 1, or in other words, 1. There we go. So I have a horizontal asymptote at y equals 1. I'm going to box that up as well, because otherwise I will forget. And let's see, now we can go into calculus. We're done with all the algebra. Very quick. Calculus, well, here's a quotient rule for you. Y prime is equal to derivative of the top, which is 1, times the denominator, square root of x squared minus 1, minus the numerator times the derivative of the denominator. And remember that there's a quotient rule there. So times 2x. And it's all over that denominator squared, which cleans up very nicely. It's just an x squared minus 1. All right. So let's go ahead and I'm going to multiply both numerator and denominator by the square root of x squared minus 1. In other words, add a half a power to all the x squareds minus 1s. And you would get a beautiful x squared minus 1. Let's see, minus x squared all over the quantity x squared minus 1 to the 3/2 power. All right. You can see the x squareds cancel and you get a negative 1 over the x squared minus 1 to the 3/2 power. We know that this does not exist at 1. So I'm going to just go ahead and start this at 1. Also, we know our function, its domain doesn't include the interval from 0 to 1. So I'm not going to include that. So I start my analysis of the derivative y prime at 1. Again, it's an odd function. I don't worry about the left-hand side of the graph. Note, as long as x is greater than 1, this derivative is negative. So it's always negative. That is, the function is always decreasing. Note also, we still have yet to find a single point to plot in a table to the right-hand side like we have been every other problem. This is kind of weird, but it can happen, and obviously it is. Now let's do our second derivative. There's my first derivative right here. And since it's written that way, I'm going to write it like this because it's much faster to take the derivative if I write it like this. There we go. Now I don't have to worry about a quotient rule. Take the derivative like that, the negative 3/2 will go out front, so it becomes a positive 3/2 because it's a negative times a negative. X squared minus 1 to the negative 5/2 power, then multiply that by the derivative of the interior, 2x. Clean this up. This will be, what is that? The 2's cancel, so you get 3x over the quantity x squared minus 1 to the 5/2 power. So y double prime, again, I only need the right-hand side of the graph, and it only starts, our domain on the right-hand side only starts at 1. And so I don't have to worry about that numerator becoming 0 because it only becomes 0 at 0, and that's not in our domain, so don't worry about that. And for all x values greater than 1, that second derivative is positive. So we have a positive, whoops, I will use black ink for that. We have a positive second derivative, which means it's always concave up. Believe it or not, we are done with all the computational stuff. Then I just grab my ruler and I'll throw on a y-axis in here. And I generally try to just center my y-axis. I'll do this up here too. I'll draw in my x-axis. Again, I'll try to center that. The interesting thing about this ruler is that even though it says 0 degrees, it might be a half a degree off, so it might be still slanted slightly. And I'll go ahead and draw up above my first and second derivative, and I only do a half line here because we're going to be using symmetry. All right, and now I can just erase that. And let's see. Actually, maybe I'll keep that in there while I have this. I'll label this up here y prime, and this is y double prime. And any special numbers for our number lines? Nope. Y prime is always negative, so it's always, the function's always decreasing. Y double prime is always positive, so the function's always concave up. So decreasing and concave up. Again, we don't have a single point to plot. Slight exception though, we do have one thing we can do. We have a vertical asymptote at x equals 1. So I'm going to go ahead and at least draw in where I think x equals 1 should be, and I'll just put a vertical asymptote there. So let me do that right here. I'll use a red line. I'll dash it out as much as I can, as much as I want to. And that's good enough for me. I also know that I have a horizontal asymptote at y equals 1. So I'll use that same kind of distance there, and I'll just plot in a green dashed line at y equals 1. I have a habit of using green for horizontal asymptotes and red for vertical, just because I want to. Okay, that's good enough. And I'll turn off that ruler. I'll label that asymptote. That's y equals 1. And this asymptote is x equals 1. I happen to know that my function, as x is approaching 1 from the right-hand side, our function was going to infinity. That's really the only piece of information, well, one of the only pieces of information that we have. So let's go ahead and start our function climbing off to infinity on the right-hand side of 1. I'll use blue for the function here. From that point forward, I know it's decreasing but concave up, and it wants to tend to y equals 1. So it's decreasing but concave up, and it wants to tend to a height of 1. Well, it's not going to become a height of 1, but it's going to tend to it. There's really not much else I can do here other than have my hand wiggle the screen by accident. So there we have, that's the left-hand side of the graph, or the right-hand side, sorry. Stick a pin right here and rotate it 180 degrees, and you will get the other side of the graph. And because that's it, that's just it. And so you can see right here that I've just kind of rotated this around, used a symmetry about the origin to finish out this graph. Now, if you go to like a Desmos to check this, you'll see that theirs is a little bit more like hugging right here. But as far as the calculus goes, we have done our calculus correct. We're okay. There's nothing else we need to do. If you want to plot a point, you totally can, but there's no real reason. We have everything done correctly using the calculus that we have. All right, that's it for this problem. Actually, the shortest of the problems I'm gathering.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.